Good morning, everyone. It's my pleasure to give my own welcome to all of you this day on this very nice day of celebrations, 40 ICSE conferences and the 50th anniversary of the very influential NATO conference on software engineering that was held in Garmisch. I can think of no better way of starting off these celebrations than with a talk by our first speaker this morning, Fred Brooks. Fred Brooks is a professor of computer science at the University of North Carolina at Chapel Hill. He's somebody who's very well known to our community. He's one of the few people in our community who has been recognized with the ACM Turing Award. He's also the author of at least 2 very influential publications that are read not just by all software engineering students, but probably by the vast majority of computer science students as well. I'm referring, of course, to his book, The Mythical Man Month, which is a very evocative portrait of his experiences as a project manager on the System 360 and OS 360 projects with IBM. And of course, his paper, No Silver Bullet, a very pointed examination of the role of essence and accident in software engineering. As well known as he is to our community, perhaps there are a couple of things that you don't know about Fred. First of all, he considers one of the most important decisions he made as project manager on the System 360 project to be not a software decision, at least not directly a software decision, but rather a hardware decision, and that was the decision to move from a 6-bit architecture to an 8-bit architecture. This change had the significant advantage of allowing the representation of lowercase letters in the representation of text inside the system, but it also had the negative effect of incurring an expense of $100 million for IBM because it required re-engineering the full product line of I/O devices. The second thing you might not know about Fred is that he was a keynote speaker at the very first ICSE, the National Conference on Software Engineering, which was held in Washington, D.C. in the fall of 1975. And so on this day of celebrating 40 ICSEs, I think it's only fitting that we close the loop, as it were, and invite Fred back to the stage and to hear him give his unique insights this morning about the history of software engineering. So please join me in welcoming Fred Brooks.
Okay, going up. Thank you.
Okay.
Good morning, everyone. Let me set my timer. First disclaimer is that I've tried to get the dates right. I've done a lot of looking, but I don't promise that any of the dates are completely accurate except ones I remember myself. And so don't cite my dates. And the second disclaimer, I think, will be obvious, and that is the pictures I'm going to show of people here do not represent how we look today. There's an American story of hardship, and so I'm going to cite it, and that is, you kids had it so easy compared to the early days. When I was a child, there were no school buses in town. We had to walk to school. My walk was about a mile, and we had to walk in this rain and snow, and it was uphill both ways. So I learned to program on the IBM 701 in 1952, and then I got a summer job in 1954 programming on an IBM 701, and let me tell you what it was like. We were hand coding on paper. Then somebody punched those into cards and they got fit in the 701. We had to code in binary, but we used octal abbreviations, so both opcodes and addresses were octal numbers. The addresses were absolute addresses. There were no assemblers, and so I got a piece of roofing tile that was 64 by a ceiling tile that was 64 by 64 and some matchsticks to keep track of where the live variables were and where there were empty spaces that could be used in the programming. And then one transferred the program to in that case, punch cards, or to paper tape, or to punched film, and then it ran on the machine. And with the 701, which had a mean free error time of 10 minutes, you did a rollback to drum every 5 minutes, so that when the machine dropped a bit, you could pick up where you were at least no more than 5 minutes ago. And we got 2 shots a day. Now, in my abstract, I covered this ground, but I want to do it anyway, and that is make distinction between 4 kinds of programming entities. The first is a program, and the first program, as far as we can tell, well, the first program was written for the Manchester Baby, and it takes 1 page. The best-known early programmer, so I'm starting with the 40s, this is the 1840s, was Ada Lovelace's for Babbage's analytical engine. Babbage didn't get the analytical engine built, but at least Ada got the program written. The next kind of thing is a software product. So a program is something I write and I use. A software product is something I write and you use, and it requires more work. It has to be generalized, it has to be tested, it has to be documented, and usually it has to be maintained. The next kind of entity, different in kind, is a software system, a system of many separate programs working together. And this is more work because you have to define the interfaces, and many, many, many system debugging troubles are because my understanding of at least the connotations of the interface and your understanding of the connotations of the interface are different, and they don't work. So now we have to do system integration and test. And the first example I can find of a programming system with multiple components was the GM batch operating system for the IBM 704. Bob Patrick at GM and Owen Mock at North American Aviation were the designers of this. And it had all these different components, and it improved performance on the 704 by a factor of 10. And the reason is because otherwise people were putting a job in, getting a dump out, mounting the tape, unmounting the tape. This way you put all the jobs for the whole run on one piece of tape, and the operating system would, as soon as it finished one, as soon as it finished dumping your memory because there was a divide error or whatever, then it started the next one immediately and got rid of the waste time on the computer. It also gave shorter turnaround, and there were professional operators, whereas with the earlier programming systems, you ran the machine, and you didn't know necessarily how to run the machine, and you made the mistakes in running the machine. The professional operators made their own set of mistakes, but a much, much smaller set. But there was no idle time. 40 copies were distributed among the people who had built it, but there was no support. It was not a product. And so then we come in '59 to the first software system product that I can find, and that was the Share operating system. The Share was an organization of users of scientific computers, particularly IBM scientific computers. And the Share operating system was an upgraded version of the GM operating system, which IBM distributed and which IBM took the responsibility for maintaining. So now we have a software system product, and this is the milestone. Now, software engineering, then, is the discipline of making software products, not necessarily system products, but any kind of software products that are distributed and maintained. And Margaret Hamilton is the person who coined the term, trying to make people understand that in the Apollo system, the software was much more complicated than the hardware. And so she coined the term to at least give some respectability to what it was we did, and that is the engineering. And this picture shows her in the mock-up of the Apollo cockpit, presumably debugging the software. So let me start now. I'm going to spend most of my time on the earlier parts of the period because that's the part that I remember and most of you don't. And so we'll start with the 40s. The big ideas of the 40s were machines. They were actually programmable computers. Now, Babbage's was proposed and detailed, planned could be built, and versions have now been built in 1843. But the first of the modern computers was done by Konrad Zuse, and it was done in 41. And those of us on the outside of Nazi Germany didn't know about it. And so from my point of view, the first computer was 1944, when Aiken was the architect and persuaded IBM to do the engineering of the Harvard IBM Mark I. So this was the machine that turned me on to computers. I was 13, and I read about this in the Time magazine, and my eyes lit up, and I said, that's what I want to do. And I've been blessed with the opportunity to do that my whole entire life, and to see a most amazing transformation of the world from 1944 to the present time. And then came the idea of the stored program computer, and if you have never read Burke's, Goldstein, and von Neumann's preliminary design of a calculating machine, every computer scientist and every computer science student needs to read that paper, and your mouth will fall open as you read it for the amazing amount of ideas that are important today that were packed into that very first paper. And the most important of those ideas was to store the program in the same memory with the computer. And John von Neumann conceived of the idea. Tom Kilburn and Freddie Williams at Manchester built the first working version of a little machine called the Baby that had 32 bits of memory. And Sir Maurice Wilkes, then wasn't Sir, built the first useful version of that, the EDSAC at Cambridge, in 1949. Morris is quite a character. He died at age 97. I visited his laboratory on sabbatical, spent 3 sabbaticals in his laboratory from 1975 until 2009. The last time I was visiting, I think it was 2008, he was 94. He came into the lab many days, and it was in there every week, and we had a lot of useful conversations. And he said, Fred, when you're in your 70s, you just keep on keeping on. He said, when you're in your 80s, you just keep on keeping on. But he said, Fred, the 90s are different. And I thought, God grant. All right. So now let's move on to the 50s, and now software becomes important. So the big ideas of the 50s, and there are a lot of them, the most important was the closed subroutine and David Wheeler's calling sequence, the so-called Wheeler jump, and input-output libraries of subroutines available for users of the EDSAC, and the first symbolic assembler. And from my experience living without a symbolic assembler of any kind, having a symbolic assembler is a big difference. And so these generated 51, the most important book in the history of software. The preparation of programs. There also was a paper, of course, earlier about the machine proper, but this is the preparation of programs for an electronic digital computer. So Sir Maurice is in the upper left corner, David Wheeler, who is one of the only computer scientists cited in someone else's Nobel lecture for his work doing the fast Fourier transform for Sir Martin Ryle's synthetic aperture astronomy, radio astronomy, and Stanley Gill. And now, here are the big ideas then of the 50s, besides symbolic assemblers and subroutines. Compilers, operating systems, terminals and communications, graphical displays, and block-structured programming. So the compiler story is very familiar to you. The first useful compiler was Fortran 56, and I remember what a big difference it was when that appeared on the machine. And it's very interesting because it's produced some of the best object code the compilers have ever produced. And the reason is, Backus and company realized that if my compiler's code is slower than assembly code, people won't use it because computer time was very, very scarce and expensive. And therefore, it was a crew of mathematicians, and they worked very hard. And so the very first Fortran compiler produced running code that was faster than handwritten assembly code for almost all cases. Now, sometimes you could improve an inner loop by some devious trick, but in general, the reason Fortran was successful as a compiler was because it produced competitive runtime code, and that was when the programs typically would compile in 10 minutes and run for an hour, just the inverse of today's situation where they compile for an hour and run for 10 minutes. And then Grace Murray Hopper had designed an English-like language because she said for business purposes, people are going to need to be able to write in something familiar. Now, of course, the formality of a programming language is there no matter what you dress it with. But the Flowmatic idea introduced the notion of an English language compiler and really made it possible. And then she led the group that defined COBOL, and as many of you know, COBOL is still with us today, and so is Fortran. Now, on the building of an air defense system in the 50s against the bombers that were going to come over the pole meant that the MIT Whirlwind, which was a kind of a classical little von Neumann scientific computer with 12-bit word size, was designed as a prototype for the air defense system. And the air defense system was, in fact, put in place on a prototype region over Cape Cod in 1953. So it already had terminals, it already had communications, it already had graphical displays. Then the SAGE defense system was manufactured and installed on a large basis. A typical SAGE computer would occupy 2 stories of a blockhouse. It was a dual machine, so in case of trouble, it would switch over. It's the largest, physically largest computer ever built. And there were 125 consoles for the people who controlled both studying the radar for the inbound attack and controlling the weapon assignment for each of the individual interceptors and anti-aircraft systems. So much for the 50s. Big ideas of the 60s. Software engineering as engineering. And so there's Margaret's contribution, and then you will have heard and you will hear more from Brian Randell about the NATO conference of '68 and of '69. And as he will almost surely tell you, the '68 conference was a really innovative and really let's all get together and try to understand how to do this. And '69 was really let's fight for my side versus your side, and there were more than 2 sides, so it was a fractious conference. An important idea, there are 2 important ideas that came along then were the multi-programming and time sharing. So Fritz Bauer conceived of the idea, as far as we can tell, of having the NATO conference, and he gave it the provocative name of software engineering techniques. It was provocative because the very notion, the term had been coined, but the very notion that writing programs was an engineering discipline was not generally accepted. And so the notion of naming the conference a software engineering conference was to get people to think about this strange fact. At the conference, the essential problem was the recognition of the software crisis. Now, I worked on operating system 360. I was in charge of the hardware from '61 till '64. And then we had the machines released into the factory, and my boss said, well, the operating system we're building is in trouble. Why don't you go over and run that for the year before you go to Chapel Hill? And so I had been through software crisis. We slipped, as far as useful delivery was concerned, we slipped a year. And so by '65, I already knew about the software engineering crisis. Didn't have to be told in '68. But Other people had experienced it worldwide. Everybody building big systems. Everybody building big systems seems to have run into the fact that the growth is not linear. The effort, the complexity involves interactions, and interactions combine combinatorially. And so things that you thought you could extrapolate linearly, you couldn't. So the 68 conference, and Brian will tell you more, was about, okay, what do we do about the fact that we have so much trouble building big systems? Now, not everybody had trouble building, not everybody had failed big systems, but everybody had had trouble building big systems. And then the 69 conference, the idea, and this is the book of the 69 conference, to give, and the 68th conference was mostly about how do you manage projects? And the 69 conference was about, okay, now what kind of techniques can we develop that will help improve the software engineering process? So it was essentially much more technical. And surprisingly enough, the conference about techniques was more fractious than the conference about politics and people management. That is surprising. Well, all right. Now, the first multi-programming system that I know about was built by Ted Codd, and that name will be familiar to you for his later work on relational databases. But he built a system for the Stretch supercomputer. Now, Stretch was the world's fastest machine from 1961 to 1964. We built 9 of them. We sold them for $10 million apiece. It was sold to atomic energy commissions and to weather bureaus, principally worldwide, Britain, France, U.S. It stood about 5 feet high, 5 feet deep, 15 feet long. We built a 20-foot plug-in card for the National Security Agency that added on to it. But this was the first machine that had hardware for operating systems. So it had memory protection, it had programmable interrupt, it had a time clock that could do interrupt, and it had supervisory mode. And so Ted said, well, look, now that I've got this thing, I can build a multi-programming system which will enable one job when it's slowed down waiting for I/O, for the CPU to go ahead and be doing computing on the other job. So the purpose of this was overlapping I/O and compute, not time sharing. But he built it and he made it work. So Christopher Strachey announced at the end of one conference, you know, it's time we ought to be able to build a multi-programming system. And Ted Codd stood up at the end of the conference and said, and we have one running. So it was very nice. Now, Ted did such a good job that I did the most useful thing I ever did at IBM, I think, and that on behalf of the company, and that is I paid to send him to graduate school to get a PhD, and that's where the relational database work was done. So, meanwhile, the idea of really making time-sharing systems was introduced at Manchester by Kilburn and Company, and first done on the Atlas computer that Manchester had built. This machine had paging, and it enabled their supervisor was designed to enable interactive debugging. So that's the ancestor, really, of all of today's operating systems. This gave the idea, meanwhile, at MIT, they were building one in competition for Corby on an IBM 7090, and that seemed like such a good idea that they would build a version of this called Multics, which was built for the GE 645, a machine that never had too much traction and didn't go too far. But Multics had many important ideas in it. It was a major project, and it came out, I think, 65. Whoops. Okay. Now, the other set of big ideas that I would point you to from the 60s were classes and inheritance, and database systems and the whole idea of doing formal verification of programs. So the notion of classes and inheritance were introduced in the Simula 67 system by Kristen Nygaard and Ole Johnson Dahl, and we see them both here. Simula was designed as a simulation program, but this idea was so much more important and so much farther reaching that we don't even remember, especially Simula, but we do remember these fundamental concepts. Database systems, Charles Bachman designed a navigational database model in which the integrated data store, and Ted Codd came up 5 years later with the relational model, which is more popular today. The notion that we can prove things about theorems starts fairly early. So Bob Floyd wrote a paper assigning meanings to programs and showed that you could do proof. And then Tony Hoare came up 2 years later with an axiomatic basis for computer programming. So today, the really crucial programs, one has to formally verify the kernel, and this is true of airplane programs, and this is true of autocar programs, because no matter what we do, we cannot test all the bugs out of a programming system. So now we move on to the 70s, and here's some big ideas from the 70s. Information hiding, modules, abstract data types, the notion that we can build top-down by incremental refinement. Notice that some of these are conceptual ideas and some of these are process ideas. Inspections and software engineering management as a discipline. So David Parnas, who is a wonderfully provocative character for fun, came up with the idea of information hiding. And he and I had a long debate on this, and it's invited in the second edition of the Mythical Man Month. And he was right and I was wrong. And his basic idea was you ought to have a program divided into modules. The interface ought to be defined as to what the legitimate inputs are, what the expected outputs are, and what the valid operations are. And then how it's done inside the module should not be visible from the outside, no matter what you do. We had built the operating system using control blocks in which every part of the program consulted the same control blocks to get the shared data. And so you could update the shared information by updating the control block. But it turned out that different people would update the control blocks wrong and wouldn't necessarily set the signals right, and Parnas was right and I was wrong. Now, Parnas's idea was then generalized, and Barbara Liskov had, I think, the first important paper in the abstract data types. And I love this little cartoon that says, "Sure, I got principles. You want to see my Liskov substitution?" All right. So that was a proposed mechanism she had for using the abstract data types. And this magazine picked up on that, the OOP girls. All right. Top-down, incremental build, and stepwise refinement. Harlan Mills was one of the great pioneers of the early software days, with many important ideas, and one of them was incremental build. He said, and he was working principally with real-time systems, he said, build an inner loop that doesn't do anything, except it has stubs for calls. And then one by one, you populate the stubs, and you test at every stage. So this is a incremental build approach in which you know you're right all the time. And he said, go ahead and deliver to a customer the very first version of that that's populated enough to do anything useful for them. Why is that important? Because the customer will want to do things you didn't think of. and the customer will find ways to mess up your system, that misuse your system that you didn't think of. So the sooner you can get a prototype running system into the customer's hands, into the user's hands, the sooner you will get the feedback back. This principle is so important that today we understand that, and we still don't always practice it. Klaus Wirth came, and Klaus said, "How do you pronounce my name?" He said, "If you call by name, it's Wirth. If you call by value, it's worth." When I like that. Klaus proposed stepwise refinement as a different concept from incremental build. It's a notion in which you may start with a sketch of the whole program, and then stepwise you improve the sketches. One of the important ideas introduced at this time in process was inspections, and Michael Fagan proposed this, having a formal team of outside inspectors go through the code, reading it line by line out loud, working against a set of specific requirements. So part of this is getting a set of specific requirements. And then the team of auditors essentially look at the code to see if it satisfies the requirements, as well as to look at internal defects. I'm not sure the degree to which this is practiced today. I think it's an important idea. And then the other idea from this 70s period was it's time to start realizing that this is a management problem. And some of you are familiar with my book on the Mythical Man Month, which essentially people say, "Look, why is that book still selling today? About 10,000 copies a year. It's been 43 years since that book came out. Is it obsolete?" Yes, some of the chapters are absolutely, ludicrously obsolete, like how to get stuff into a 4K memory and so forth. And some of it is not ridiculously obsolete. And why? Because the book is not really about technology. It's really about people, and the people haven't changed very much. The stage keeps changing, but the script doesn't change much. The other important idea from the 70s, and Barry's here, we had a good conversation last night. I hope you'll get a chance to talk with him, is requirements verifying and validating. The verification is, am I getting the requirements right? That is, are they complete? Are they consistent? Is the thing that's being asked for feasible in terms of cost? Testability. And validation. Am I building the right product at all? That's a really crucial one. And so, no silver bullet paper you're familiar with, and it says software is essentially hard to build. And I'm going to restate a statement I made in '85. There's no single development in technology or management which alone promises a 10 times gain in 10 years, and I'll state that in 2018, good for the next 10 years. And so that concludes me, and I will then aim you at some important resources. If you have not seen Grady Booch's ACM webinar on the history of software engineering that starts at the beginning and goes up to the current, you should. And then the most important literature is the book that includes Barry Beam's lifeline contributions, very important papers to development, software development research. I think there's probably no book that's more useful in today's software engineering than the book of Barry's collected papers. And the other one is Hoffman and Weiss's collected papers of David Parnas. So these two giants stand tall across the decades in terms of the depth of their thinking, the breadth of their thinking, and the clarity of their thinking. So I would encourage you, if you're going to read anything, read Beam and Parnas. And with that, let me conclude. Take questions.
Thank you very much, Fred, for that, that very nice tour through the history of software engineering. So we have time for questions. We have 2 microphones here in the front and also a couple of microphones up there in the aisle up there. So please come forward to one of the mics if you'd like to ask Fred a question. Give people a little bit of time to head to the microphones.
Can I?
Sure.
Go ahead.
Here, yes. I would like to ask you, do you see that there will be some big change in the future in software engineering, thinking about the new technologies, AI and such, or it's repeating the same thing?
AI is going to change things, and we don't know how. The key to almost all the useful AI today is big data input. And the only big data we have today that is relevant is massive code bases. And how we harness that, I have no idea. But we will see that develop. And my skill as a prophet is very poor. Morris Wilkes' engineering judgment and what he said 50 years ago about technologies is just incredibly on track. I was amazed talking to him. But I'm not that good a prognosticator. I'll stand by my 10-year prediction, but I'll stop there.
Okay, we have a question over here.
Yeah, I was wondering the relevance of the decision when IBM was forced to unbundle their software from the hardware as part of the Federal Trade Commission court case. That seemed to me strategically very important because for the first time we actually got a market for software, which we hadn't really had until then. And how would you see that as being important?
Well, it did change everything in the sense of market, and it meant that there was a room for competitors, essentially, and therefore free players. I think that competitively, having competitors is a healthy thing for the development of a technology. From the point of view of IBM, it removed a lot of burden. It meant that IBM still had to support the products and had to maintain the software, but at least they could collect separate revenue for that and could identify then the revenue to cost return. Whereas before there was an unlimited demand for software and there was no reason for the customer to limit the demand. There was no price, okay? And so from the point of view of one responsible for building a system to satisfy thousands and thousands of customers across all kinds of applications, that's kind of frightening. And that was before unbundling. So, yeah.
I mean, an interesting corollary to that is that when IBM negotiated the deal with Microsoft to source DOS, they never asked for the source code. Because I believe at that time IBM thought, no, the money's all in the hardware. They'll never make money out of software.
Well, IBM's whole PC story is kind of sad to start with from IBM's point of view. To give away the processor to Intel and to give away the operating system to Microsoft doesn't leave you a whole lot to collect money on.
Okay.
Okay, so first, thanks a lot for your presentation. It was really inspiring. See all the history of computer science unraveling under our eyes was fantastic. I once heard somebody saying that he who doesn't know history is condemned to make the same mistakes again.
Santayana, yes.
And so this is very important to collect the history of how we developed software. I have initiated a few years ago a project whose code name is Software Heritage. We are building the archive of every piece of software ever built. So my question for you is, do you believe some of the very important software systems you are mentioning here are still around somewhere? Is it still possible to find the source code of this? Do you think it is possible to collect it and make it available for people to study it?
I don't know, but I know where you would ask. There's the Computer History Museum in Mountain View, California, and they have a collection. And there's the Computer History Museum in Minnesota, and they are especially strong on collecting documents. The California one is stronger on artifacts, but they also collect code. So those are the places I would look for the materials to be archived, and whether you have any way to, whether you have the assemblers and whatnot to analyze the code, if you have the source code, I don't know. Okay.
Okay, so thanks a lot. I know very well then Schuster, so but the question was, for example, would IBM be open to share the source code?
I haven't been associated with IBM since 1965.
Okay.
I've worked as a consultant and on their technical committee, but I haven't had any management responsibility there.
Okay.
So I have no idea to what they're open to.
Okay, thanks anyway.
Okay, do we have a question in the back there? Nope. I don't see anybody else. Okay.
Okay.
Well, thank you once again, Fred, for a very enjoyable talk.